Okay, welcome everybody to this month's installment of the AI Presents seminar series. Today we have Feliks Nüske from the Max Planck Institute in Magdeburg. Feliks Nüske has a PhD from the Freie Universität in Berlin. And after he finished his PhD, he moved to the beautiful city of Houston in the US. And then he moved to do a postdoc. And then afterwards, he moved to Paderborn University for a few years for a postdoc, and now he's a group leader since 2 years in Magdeburg. And we're very much looking forward to what he has to say today, or tell us today about kernel methods for Koopman-based modeling of molecular simulation. So please take away, Feliks.
All right, thank you. Thank you so much for coming and for the invitation. Yeah, I want to give you guys a bit of an overview about some of the methods revolving around the Koopman operator framework that I've been working on over the past years and some of their application to molecular simulation. So, I mean, one of the long-standing goals that I guess many of you are familiar with is to analyze metastable systems, which frequently appear for molecular simulation. First, standard model problem is to analyze these so-called overdamped or just Langevin dynamics, which is the stochastic differential equation driven by the negative gradient of some potential plus random noise controlled by temperature in physical applications. And we all know that if the energy has certain deep minima separated by wells and the noise level is relatively small compared to the size of the barriers, then the system will be metastable. And we expect to find that basically the neighborhoods of these minima are long-lived states, and it takes the system a long time to transition across these barriers. We would like to devise methods that can automatically determine how long it takes on average to transition from one state to the other, and also just to find the decomposition, which is pictorially shown here for the 2D system on the right. Yeah, we ideally like to assign data points to metastable sets so we can distinguish them. Yeah, because for a system that is not 2D like this beautiful one here, we cannot just plot the entire state space of the system and determine what the states look like. Okay, so I have 4 parts. First part is a brief general introduction to the Koopman operator framework, what it is, quite independent of molecular simulation. Then I want to introduce the variational approach, which I assume that quite a few of you will have heard about, which allows us to characterize the metastable states and corresponding transition rates in terms of eigenvalues of the Koopman operator in that specific setting. Then I will talk a bit about learning the generator that is associated to the Koopman operator and what we can do with it. And finally, I want to show you what I promised in the title, namely how you can use kernel methods in combination with the Koopman operator framework. All right, so what is Koopman about? The workhorse algorithm for Koopman framework is called extended dynamic mode decomposition, or EDMD. And I like to motivate it by the idea that we have some dynamical system. Again, it doesn't have to be molecular simulation at this point. And we would like to learn a predictive model for this system. But well, we want to be a little smarter than just applying linear regression to the system itself, because probably if the system itself is non-linear, then learning a linear map to predict the state is not going to help us much. So the trick of EDMD is to define a set of, there are different names around, observables, sometimes called the dictionary, whatever it is. It's just a collection of functions of the state space. We pick a finite number of functions of the state space. Let's call them observables for now. And we want to find a model that allows us to predict the state of these functions as time progresses under the evolution of the dynamical system. And the straightforward way to devise a learning algorithm is just to do linear least squares. So let's say we collect samples, we collect pairs of data points, xk and yk. And we assume that each of these every pair of xk, yk samples is separated by a fixed amount of time, which we call the lag time, and I denote it by t here. And then we assemble 2 matrices, where in each of these matrices we assemble all the basis functions either at all of the x data points, think of it as the initial data points, and then the same with the same basis functions evaluated all these terminal data points, all the ones that are separated by the initial ones by time t. And these are the 2 collections of data on which we apply linear regression. Yeah, we want to find a linear predictor for the dynamics of these observable functions under the dynamics. And since it's a linear regression problem, we can solve it directly, can apply the pseudo inverse of the matrix psi of x, that's this one, to the target matrix psi of y that defines an optimal matrix, and that's what we call KT. Okay, this is what EDMD does.
Sorry, I was just here, and I think I dropped the red. Thank you. Can you just throw it to me? This one? No, the. It's in the corner, like exactly in the corner. Okay. Sorry.
No bother.
Thank you very much. Thank you. Questions?
Okay, on a more serious note though, if you have questions, just stop me, okay? Good. Okay, so that's the basic EDMD algorithm. Now let's try to understand why this is actually a good idea and why it's a better idea than trying to fit a linear regressor to a nonlinear problem. And in order to understand that, we have to take a look at a statistical limit of these two factors, of these two matrices. And let me go back quickly once again. In the expression, in the analytical solution of the linear regression problem, we have two matrices. Yeah, one of them is, well, to take it away, it's like it's an instantaneous correlation matrix between the basis functions over all the initial data points, and then we have a time-shifted correlation matrix here, right? So let's take a look at the statistical limit. And then assuming that these x data points, these initial conditions, come from some distribution rho, we don't need to know it, it just needs to be some probability distribution underneath, and by law of large numbers, this matrix will converge to what we usually call a Gramian matrix or mass matrix for these basis functions for these dictionary functions that we have selected. And importantly, the time-shifted one converges to something similar, but it contains the object that I've highlighted here. It contains a map that maps a basis function to a conditional expectation of this basis function at time t, given some initial condition. And there are two important properties of this operation that we need to recognize. First of all, it maps a function to a new function because it still depends on the initial condition x. Yeah, a conditional expectation depends on the initial condition x. So it's a map from function to function, and it's linear, right? Because it's just an expectation value. So it's a linear operation, a linear operator on functions. And with this insight, we understand that what EDMD is doing in the statistical limit is that it learns what in PD theory would be called a Galerkin approximation. Yeah, it learns learns a mass matrix and a stiffness matrix for a linear operator, and that linear operator is called the Koopman operator. That's this conditional expectation operator. Yeah, so just again to repeat it once again, EDMD in the statistical limit learns a projection of the Koopman operator onto a finite dimensional basis that we have selected. And therefore it makes sense to expect that if we increase the basis set, if we increase the set of observables that we use, we actually learn a meaningful model. Yeah, we learn an approximation for this linear operator, which just by looking at it, we can already see that this contains a lot of useful information about the system, right? Because it allows us a glimpse into the future. Yeah, it allows us to compute or to predict the statistics of observable functions in the future, right? Okay, good. So people often explain or summarize the scheme once again like this. So we have a nonlinear dynamical system, but in finite dimensional space. That's the state space. We collect data. Again, these are these time-shifted pairs of observations. That's easy to do. Then we solve a very simple linear regression problem. It's also easy to do. But now we understand that what we've done is we have taken a linear operator, which basically maps the nonlinear system on finite dimensional space to a linear dynamical system, but in function space, so infinite dimensional space. This step is usually called the lifting of the inherent in the Koopman framework. And then we have made it finite dimensional again by the choice of a finite dimensional trial space or Galerkin subspace. All right. Do you guys have any questions on this part so far? All right, good. And I just wanted to highlight that what I think is a very familiar model, probably to many of you, is just a special case, namely the Markov state model. Markov state model fits into this framework by choosing our dictionary as a set of piecewise constant functions. Yeah, if this is our state space and we somehow divide it up into non-overlapping sets, indicated by these dashed lines here. And if we then take a dictionary where we have one function for each discrete set here, each state, and it's just one on this whenever I'm inside the set and zero everywhere else. Yeah, so it's piecewise, a step function, piecewise constant function. And if I plug this function into the two constituent matrices that we just wrote down, then we see that the mass matrix is a diagonal matrix, which contains the total number of visits to each state on the diagonal, and the stiffness matrix is what we usually call the count matrix in MSM estimation. And then if I take the inverse of this guy times the second guy, I get the standard maximum likelihood estimator for the Markov model transition matrix. Yeah, so it fits into this framework as a neat special case. All right, good. So much about the basic EDMD framework. I mean, and the main reason I'm introducing it is because I just want to bring across that it's a much more general framework. Yeah, just much more general than just Markov state models for molecular kinetics. Yeah, whenever we use any variant of this algorithm, we really learn a model for an operator that is a predictor for the statistics of the system in the future. Yes, please. Yes.
Hi, one question. Is this concept or this Koopman operator related to these state space models that one hears about now that go in the same direction as transformer models, but having a different mechanism for the attention? So are these state space models related to this Koopman operator ansatz or not at all?
Oh, to be honest, I don't know, because I don't know much about these state space models. Sorry about that.
Okay. Thank you.
And how is the basis chosen, or like the observables, how are those chosen?
That's, of course, the million-dollar question, and we'll talk about some ideas in the last part of the talk. Okay? Yeah. Okay. Now, second part I want to discuss is the variational approach, which already to some extent goes into that direction, but it is mainly the connection that allows us to use Koopman models to analyze metastability. Right? I mean, that's where we started out. So from now on, let's make life relatively simple and specify the type of dynamical system we want to study. What we want to study now is we want to study a reversible dynamical system. You know, think of typical reversible molecular dynamics with an invariant measure mu, which is typically the Boltzmann distribution in molecular simulation. And the reason we introduce these two ingredients is that then the Koopman operator on a suitable function space becomes self-adjoint, symmetric in that inner product weighted by the invariant distribution. So self-adjoint operators are extremely useful because they have much more powerful properties than general linear operators. Think of the distinction between symmetric matrices and arbitrary matrices. For symmetric matrices, there's a lot more you can do. And in fact, we can make use of one of these typical properties that we also have for symmetric matrices, of course. Namely, we know for self-adjoint operators, any eigenvalue, if it exists, it must be a real number. We cannot have any complex eigenvalues for self-adjoint operators. And the key to understanding metastability in terms of the spectrum, in terms of the eigenvalues of the Koopman operator, is to study the dominant eigenvalues. It's easy to show that there is always a dominant eigenvalue equal to 1. And if you plug in some more assumptions, it's also reasonable to show that it is isolated. So there's just a single non-degenerate eigenvalue 1. And then the claim is, or the fact is, that the system is metastable if this dominant eigenvalue 1 is followed by basically a cluster of eigenvalues which are close to 1. And ideally, you have some sort of a spectral separation between this leading cluster of eigenvalues and all the rest. Why is that? Let me just give you an intuitive explanation. If your system is metastable, then again, recall what the Koopman operator tells you. It predicts the expectation of some observable over some amount of time later, right? After you've let your system run over a certain amount of time. Now, in this setup that we've described, this conditional expectation, regardless of what the observable is, for any observable is eventually going to converge to just the stationary expectation of your observable, just to the expectation of your observable with respect to the invariant measure. In the long term, if I make the lag time extremely long, regardless of your initial position, this conditional expectation is going to be equal to the equilibrium expectation of your observable function. Yeah, and that's one of the key properties of an invariant measure. Right? So eventually, as a function of your initial condition, the application of the Koopman operator leads you to a constant function, because the system just forgets where you started over an extremely long time. But if it is metastable, then there have to be some observables, for example, functions that are extremely localized on one of the metastable sets, for which this expectation decays slowly towards the stationary expectation. And that means there have to be some eigenvalues which are close to 1, at least for a reasonably large span of lag times. Yeah, does this explanation make sense? Because if it wasn't metastable, then all conditional expectations would just quickly decay towards the equilibrium expectations, because the system quickly forgets about its initial position. Yeah, for me, that's the intuitive explanation for why we expect the spectral cluster around 1. Okay, and now, well, since the Koopman operator is self-adjoint, we have what's called a variational principle. And the variational principle tells us that I can take the true first, let's say, m or m+1 if I start at 0, first m+1 eigenvalues of my Koopman operator. So what I have on the right-hand side here is the sum of the first m+1 exact eigenvalues of the Koopman operator, which I don't know, of course. But we know that this number is bounded by a quantity that I can define in terms of any selection of functions, of observable functions. And to calculate that quantity, I need to pick the same amount of functions. I need to pick m+1 functions, which are mutually orthonormal. That's the second condition here. They're mutually orthonormal in function space. And I evaluate this sum of matrix elements between these functions with the Koopman operator squeezed in the middle. Yeah, these sum of sandwiches with the Koopman operator, or more technically, the sum of autocorrelation functions for the selected functions phi I. And the variational principle tells me that if I basically vary the selection of these m+1 functions subject to the right orthonormality condition, and always calculate the sum of autocorrelation functions, it is always bounded from above by the true sum of eigenvalues. Yeah, so I have a natural analytical upper limit to this quantity here. Therefore, I can maximize this quantity in order to find a better and better approximation of the true eigenfunctions. Yeah, and equality holds if and only if we pick the true first m+1 eigenfunctions as the candidates here. Okay. They naturally satisfy the orthogonality conditions as well. And the reason why this variational principle has been so interesting and so successful is that the quantities appearing here, so both the normalization condition as well as these autocorrelation functions, are precisely the numbers we've already encountered in the EDMD algorithm. Yeah, they're correlation functions. The normalization condition is an instantaneous correlation function between two trial functions, and likewise, I already call them autocorrelation functions, and that's exactly what they are. Yeah, I can approximate these numbers, these matrix elements, by computing a time-shifted expectation between those two functions. Yeah. So I can use data to calculate both the constraint and the objective function, and then systematically vary my choice of ansatz function here, and try to maximize this left-hand side here in order to find an optimal approximation. Yes, please.
Can you say again what M is?
M is a number I pick. It's the number of eigenvalues close to 1. Yeah, and it corresponds to the number of metastable states. So usually I don't know it in advance. So I have to look at my Koopman spectrum and see if I find a spectral gap or any spectral signature that allows me to choose M. It's not always easy. Yeah. It works well for toy problems. For molecular problems, it's more difficult. But it's the number of metastable states.
In principle, holds for all M.
In principle, it holds for all M, with this very slight technical caveat that in principle, there can be a point where the spectrum of the Koopman operator becomes continuous. Technically it's possible. and then this whole approach would break down. But in usually that doesn't happen. Okay, good. Okay, but the interest in this idea was really we have a data-driven but still principled guideline which we can use to optimize metastability, or to optimally learn and analyze metastability. And I mean, well, how do you pick these candidate functions phi I now? There's different approaches that have been suggested, but the simplest thing that I just briefly want to show you is we could first select some large library of functions. I call them psi j here. I imagine that you come up with some big, but still finite dimensional space. And you just try to model the optimal approximations to the eigenfunctions as some linear combinations of your, let me again call them basis functions. Yeah, and then the problem I showed you on the previous slide, it just breaks down to finding optimal expansion coefficients for your approximate eigenfunctions in terms of the much larger basis set you have selected. And I guess it's not hard to see or hard to believe that the optimization problem turns into a matrix eigenvalue problem. Yeah, but you need to calculate the leading eigenvalues and eigenvector of a generalized matrix eigenvalue problem. Yeah, it's very similar to a standard matrix eigenvalue problem, only that we also have a matrix on the right-hand side. And the two matrices contain what one would probably expect. They contain, again, the instantaneous and time-shifted correlation functions between all the basis functions in our initial library. So another way of saying this is if we basically posit a linear model for the optimal approximations to the eigenfunctions, we get a linear matrix problem, generalized eigenvalue problem that we need to solve in the end. And I mean, this was the initial approach that we suggested in these works here. It's already been a while now. And later on, extensions using nonlinear models for the optimal eigenfunctions have been suggested quite successfully in the literature, especially deep learning framework was suggested in this 2018 paper here, which is worth reading for sure. But I mean, this was the initial idea, and that's the general framework. All right. Good. Let's keep this in mind. Yeah, so this is the approximation framework we can use to analyze metastability using the Koopman operator. And especially keep in mind that we have to solve this generalized eigenvalue problem. Yeah, because we'll return to it in the last part of the talk when we finally, for real, discuss the question, how do we choose these basis functions here? Yeah, we have still postponed this for the moment. But before we do this, let me show you a different topic also related to Koopman operators, which I mainly want to include in order to show once again that Koopman is really just much more than analyzing metastability. And that's about generator learning. Well, I mentioned in the beginning of the talk that for Koopman we have this lifting of the nonlinear dynamical system in finite dimensional space to a linear dynamical system in infinite dimensional space, in function space. And if there's a linear dynamics, then there has to be some linear operator governing this dynamics. This guy is called the generator, I denoted by L. Yeah, and it's defined literally as what one would expect. It's something like the derivative of the Koopman operator with respect to the time lag. Yeah, the Koopman operators are, you can think of them as a parameterized family of linear operators, parameterized by what we call the lag time. And nothing stops me from taking a derivative of the Koopman operators with respect to this time lag. The result is again a linear operator, which on the technical level is much harder to handle because it becomes typically becomes an unbounded operator. So if you do the analysis of this operator, you have to be really careful. But at the moment, nothing stops us from just defining it as the derivative of our Koopman operator with respect to the lag time. And then indeed, we have this linear differential equation in function space for the application of kt to any basis function. Yeah, that's what way back when I showed this diagram, I meant by linear dynamics in function space. Yeah, this is the equation. If your dynamic system is very general, it might be very, very hard to have any idea what this generator looks like. But fortunately for systems that we're typically interested in, like stochastic differential equation, then we have a lot of analytical tools at our disposal that help us to write down an explicit expression for the generator. Namely, E2 calculus tells us that for SDEs, for stochastic differential equation, the generator is a second order partial differential operator. And it has a first order term where we have the gradient of the function it's acting on, and a second order term where we have the Laplacian of that function it's acting on. And the coefficients of the second order operator are basically known if you know the SDE. Yeah, if we know the SDE, they're known. They're essentially the drift and the diffusion term in the SDE. So for Overdamped-Langevin, the model system I mentioned in the beginning, the first order coefficient is just the force, the negative gradient of the potential, and the coefficient for the Laplacian is a constant related to the temperature. So the noise intensity in your SDE. And then that means that if I have any function, any basis function, let's say, and some point, like a data point, it's easy to evaluate the action of the generator on this function at a point. Yeah? So calculating L applied to a basis function evaluated at some point is easy. I just plug in the derivatives of my basis function and the coefficients of the SDE into this formula, and I just can't calculate that straightforwardly. But that doesn't mean that we have direct access to any interesting properties of the generator, like its eigenvalues, for example. Just the fact that you can evaluate some partial differential operator doesn't give you any meaningful information about its spectrum or whatever you might be interested in the solution to boundary value problem. But again, we can play this regression game that we did for the Koopman operator. We can do exactly the same thing. We can compile if we have some data set sampling an interesting distribution, like the Boltzmann distribution, we can evaluate all our basis functions at all the data points and do the same with the generator and then play the regression game. And that results in a matrix that represents the action of the generator on a function contained in this finite-dimensional trial space. And the same arguments that I made about the statistical limit, about convergence to a Galerkin projection of the generator, hold in exactly the same way for the generator. Yeah, so our EDMD algorithm modified for the generator also provides us in the statistical limit with a projection of the generator on a finite-dimensional subspace. Okay. Now, there's certainly many potential ways a model for the generator could be used. But the one I would like to show is to basically analyze coarse grainings. So let me explain what I mean by coarse graining. Coarse graining, I just mean that we take our full dynamical system or full molecular system and we project it onto some lower dimensional coordinates. These could be very simple coordinates like center of mass of all the atoms in our molecules, but it could also be something much more complicated like a dihedral angle or collection of dihedral angles. In any case, the coarse graining can be abstractly, it can be thought of as some function that maps the full space, the full configuration space of the system to some lower dimensional space, right? That's all we need to formalize this. Now, let me introduce one object that's called it's also called projection. It's not exactly the same as the function space projection we were talking about earlier. This projection here, what it does is it averages some function over all points that are mapped into the same coarse-grained configuration. Yeah, so here Z is some configuration in the lower dimensional space. And since you're mapping high dimensional to lower dimensional, there will be an entire set, typically something like a manifold of points that are mapped into the same Z value in coarse-grained space. And this operator here takes a function and averages it over every such manifold. Yeah, so in the end, you have a new function that only depends on the coarse-grained representation. That's the Z value here. And it turns out that if you now take the original generator of your original dynamical system in full space and apply this projection on both sides, what you get is again the generator of an SDE. I mean, this is not non-trivial to show, but people have shown it. If you apply this averaging principle, the resulting operator is again the second order partial differential operator, which corresponds to an SDE in coarse grain space in Z space. Yeah, so there is some SDE in Z space with some effective drift and some effective diffusion, such that the generator its generator is the result of projecting the full generator by this averaging map. Okay, I didn't show this. This is non-trivial, but it's a fact. And so that means applying projections to the original generator gives us access or an inroads to some coarse-grained SDE, yeah, that we can attempt to use to replace the full SDE in some lower dimensional space. Yes.
How is it related to this transit model?
Yes, it is related. It's the outcome you get if you ignore the memory kernel. Yeah? Because this equation is, of course, it's memory free, right? It's again a Markov process in Z space. So if you're willing to sacrifice the memory part, this is what you get.
But you get a position, it's a state-dependent diffusion constant as far as I can see, right?
Yes, this can very well happen. Yeah, even if your original dynamics was of constant diffusion type, this one might be state dependent.
But I guess the memory text at least partially.
You can, yeah, you can certainly I don't know, augment this framework to also include the memory effects. Yeah, but at the moment, if you do it at face value like this, you're sacrificing these.
You don't incur any errors in this. The dynamics, the spectrum will still capture the right spectrum.
No. The spectrum in general, without any assumptions, if you choose some xi, the spectrum might be completely different. But where you can show some consistency results. Yeah, in fact, I mean, that was one of my works when one can show that if the projection error of the true Koopman eigenfunctions on this xi map is small, then you also have control over the corresponding eigenvalue error between L xi and the true generator. Yeah, exactly, makes perfect sense. Okay, good. Okay, so we have this framework that allows us to describe the generator of an effective SDE, of a coarse-grained SDE. And now another important equality that was shown years earlier is if I take some basis functions that are in fact functions of the coarse-grained space only. If you can write your basis function psi I as psi I of xi of x. It only depends on the value of my coarse-graining map. Then, which is something that we routinely do, right? This is something we do all the time, right? We always choose basis functions or even state definitions in Markov state modeling as a function of some feature coordinate, right? Of some dihedral or some distance. Yeah, so it's a routine operation. Then we have an identity connecting inner products for the generator in full space with respect to the true, I'll just say to the true Boltzmann distribution, and inner products for the effective generator with regard to a projective effective invariant measure. So these two are exchangeable. Yeah, there's some change of variables formula that's going into this. Okay, and this means, I mean, that's once you have this, it's easy to argue that if we have data from sampling the full system, if we have generated a molecular dynamic simulation sampling the full system, but we use an algorithm like our EDMD method with a basis set that actually acts only on some coarse-grained variable, then if I apply the EDMD method, I'm simultaneously learning a model for the full generator and for the coarse-grained generator. Yeah? And that means that by varying the xi map, I can systematically evaluate the quality of some coarse graining, right? I can, for every choice of xi, I can come up with some canonical dictionary, compute this approximation to the effective generator, diagonalize it, and then I can compare the eigenvalues as a function of xi. Yeah, so this is one example of how it's a completely different aspect of the whole Koopman EDMD framework can be used to solve, or to, let's say, not solve, to approach an important problem in molecular dynamics, namely how do we choose a coarse-grained function. And a study we did a few years back in that vein, in that spirit, was we used the fact that if we have a reversible system, then we can express this matrix element for the coarse-grained generator as an integral in coarse-grained space that only contains basis functions and the diffusion. Yeah, the rest is implicitly incorporated in the effective invariant measure. And now I can take some parametric model for the diffusion, plug this in here, and basically compare these values to some reference values that I obtained from the full simulation. Yeah, so what we did here is, I know this is a bit fast now, but what we did here is we just took we first used some EDMD model to approximate the leading eigenfunctions of the full Koopman operator using the methods I just showed you in the previous part. And if they are good, if these are good eigenfunctions, then applying the generator to such an eigenfunction should just be an eigenvalue times the same function, right? So that gives me a reference to compare to. Then I pick these eigenfunctions and a number of test functions, and I vary my parametric model for the diffusion in order to optimally reproduce the spectrum. And that's why we call it spectral matching, because what we're doing is we're trying to find an effective diffusion which reproduces the dominant spectrum of the Koopman operator. And for a simple alanine dipeptide in 2 dimensions, it seemed to work reasonably well. We use the 2 canonical dihedral angles of alanine dipeptide as the coarse graining map. We chose some Gaussian basis functions here to model the diffusion. So the diffusion here is a linear combination of Gaussian basis functions. We solved this regression problem with regard to the spectrum we obtained from the true Koopman operator, and we effectively showed that we can recover the 3 leading eigenvalues of the full system. Yeah, so the black dots are the reference ones we got from Koopman. The blue ones are the ones reproduced by running the learned dynamical system in 2 dimensions. And especially we compared this to just using basically a thermodynamic coarse graining method, which is called force matching. Force matching is a method that has been used a lot in the literature and it's quite successful, but it's based on learning an effective potential in coarse grain space only on reproducing the thermodynamic consistency, only on reproducing the effective Boltzmann distribution in coarse grain space. Yeah, and here we showed that including this, learning the state-dependent diffusion on top of it helps us recover the dynamical properties much better than just the coarse grain.
So what extra information that you need for this? Do you need to know the rate? Do you need to know the spectrum already of the full system?
Yes, exactly. So here you always assume you have the data from the full system. So you can run some Koopman model or MSM model, whatever you like, to extract the leading spectrum, leading eigenvalues. And then you use it to learn a consistent coarse grain dynamics.
Okay, so you learn a position-dependent diffusion.
Yes, yeah.
Okay.
Yeah. So in relation to your previous question, I mean, it's not surprising that for alanine dipeptide, we can learn a dynamically consistent effective equation in this particular coarse grain space. We know that. But the point here was to show that adding this diffusion really helps us recover the dynamics, or the dominant part of the dynamics, compared to a standard method like force matching.
But the sort of the overall hierarchy of the timescales doesn't change, right? We don't see.
Yes.
Yeah, so that's also the same for flow matching. Just basically scale.
Yes.
Yeah.
Yes. Yeah. We're making it slower. Exactly. That's what you want, right? Presumably. Okay. So how much time do I have left, by the way? 10 minutes. Okay, I'll try. Do my best. Okay, good. This was the coarse graining, and now about the kernel methods. So let's finally get or approach the topic of how to select these basis functions for EDMD. Well, as you guys already hinted at, choosing a good basis set in general is of course very difficult. And the idea behind kernel methods is to let the data define the basis. So if we have a bunch of data points, which are indicated by the red point dots here, why not just place some local bump function around each of these data points and take this as my basis set? Yeah, why not do this? So a typical choice for the bump function would be a radial basis function, yeah, so a Gaussian function, depending on the Euclidean distance between any 2 points. And I mean, the way I would incorporate this into an algorithm like EDMD is I would, for each data point that I've observed, these are the xi's, I would just fix the first argument of this radial basis function to this specific data point and leave the other one free. Yeah, leave the second argument variable. And that way I still obtain a genuine function of the state space that I can plug into my EDMD algorithm. Now, if I do this, the two matrices that I asked you guys to keep in mind can be evaluated entirely in terms of these pairwise evaluation of one single function, of this radial basis function kernel. That's just the function, the two argument function I introduced over here. Yeah, the time shift, the instantaneous and the time shifted correlation matrix break down entirely to pairwise evaluations of the same function, this radial, in this case, the radial basis function, at either of at all pairs of x data points or at all pairs of x and y data points. Yeah, and that's the appeal. Yeah, I select one function, one two-argument function, and then my EDMD matrices break down to pairwise evaluations of this single function. Yeah? And the function is always called the kernel. I don't have the time to go into the theory of this, but there's a well-established theory around so-called reproducing kernel Hilbert spaces that tells you exactly what type of functions, what type of two-argument functions K you can choose in order to generate basically a well-defined limiting space. Yeah. At the moment, if I describe the algorithms the way I just did, okay, I'm just choosing some dictionary functions defined by my data set. Yeah. But the natural question to ask then is, what happens if I let the data size go to infinity again? Do these functions defined by an infinite ensemble of data points, do they actually define some reasonable space? And what are the properties of this space? Yeah, and the answer is provided by this theory of RKHSs, reproducing kernel Hilbert spaces, which tell you exactly, they give you two conditions on the function K, such that there is a limiting space. And in many cases, for many choices of interesting kernels, including the Gaussian, the space is infinite dimensional and typically very rich in the sense that it is dense in many typical interesting function spaces. So the bottom line of this is, if I use a kernel to generate my dictionary, I'm implicitly using some infinite dimensional space in the background, which I can expect to be very large. Yeah, so I can expect it to provide good approximations of quantities I'm interested in, like eigenfunctions, etc. But a little more down to earth is the question is then what do I do with the resulting EDMD problem? Yeah, so going back to this question of metastability, we found that in order to analyze metastability, we need to solve this generalized eigenvalue problem, which now involves these two kernel matrices here. And their size is their shape is just as large as the data size, which can be tricky, right? If you have a million MD samples, then these are two 1 million by 1 million matrices, and you're asked to solve a generalized eigenvalue problem with these two matrices. That's expensive. Fortunately, in many cases, there is some hidden low-rank structure behind these matrices. So you can expect that you can find some low-rank approximation to at least one of those matrices and exploit it to bring the computational cost down again. And one way to arrive at this low-rank approximation that we investigated here is to use a well-known method from kernel methods, so from machine learning, which is called random Fourier features. Did I write it down? No. Okay. So RFF stands for random Fourier features. This theory tells us that if I have a kernel which is translation invariant, like the Gaussian kernel is invariant to translating any two data points. It only depends on the distance. Then this translation invariant kernel can effectively be expressed in terms of Fourier transforms. It can be written as the inverse Fourier transform of some generalized, of some probability measure in frequency space. What that means is that I can write it as an expectation value of simple complex exponentials. And the expectation value is in frequency space with respect to some probability distribution, which I here call it rho in the frequency space. And the important point is that for most popular kernels, this measure in frequency space is known. And it's also no surprise. If you think of the Gaussian kernel, you know that for a Gaussian, the Fourier transform is again Gaussian, just with the shape parameter inverted. So it makes sense that for the Gaussian, we know exactly what this spectral measure in frequency space is. And this similar statements hold for most popular kernels. So we can safely assume that we know what this so-called spectral measure rho in the frequency space is, and that we can cheaply generate samples from it. Well, and if we can generate samples, we can play the usual Monte Carlo game and approximate these expectation values by finite averages. Yeah? And that's where the low rankness comes in. Yeah? If we can afford to approximate these kernel evaluations by averages using a reasonable moderate number p of frequencies, which we have to draw from this frequency measure, associated to the kernel, then we're good. How does this work? Just keep in mind that we can apply this formula to all kernel evaluations at all pairs of data points, and we can use the same samples in frequency space for all the pairwise kernel evaluations. If we do this, we immediately obtain a low-rank structure of the two matrices, yeah, right? Because we can write the matrix containing all the pairwise kernel evaluations as a simple matrix product over matrices that only contain these complex exponentials, evaluated at all real space data points and all frequency space data points. Since the number of frequency space data points is moderate, it's only moderate, that's what I call P here, we have a low-rank structure for both matrices. And so we've broken down our generalized eigenvalue problem into a problem where both matrices have this product structure with a tall skinny matrix and multiplied to its Hermitian transpose. Then we can go even a bit further. At the moment, these two matrices are still m by m. They're still as large as the number of real space data points that I've observed. We can do some manipulations and show that we can basically write down a dual eigenvalue problem, which is only of the size of the sampling we do in frequency space. Yeah, so we can break them down to two matrices which scale with the number of samples in frequency space. And well, here's where we just need to assume that we can get away with a moderate number of samples in frequency space. Okay, that's the algorithm. I think in the interest of time, I can just skip it and just show you that we have some promising results. So we applied the idea to one of these typical D-Shor benchmarking systems, FIP35. It's a small protein with 35 amino acids. It's been studied many times before, and we have long equilibrium simulation data available. We also know that there's the most interesting metastable transition is the unfolding process, and we just would like to use the method I just described to find out to verify that we can characterize the folding process in this way. So, and we try to keep the method as agnostic as possible. Yeah, so we used the Gaussian kernel as usual. We decided to use a feature space, again comprised of molecular interatomic distances at angles. If you do this, you obtain a feature space of dimension roughly 600. It's just the combinatorial number of all residue distances and dihedral angles. So on this 600-dimensional space, we use the Gaussian kernel. Then we did some validation, some model validation using the variational principle to determine an optimal bandwidth of the Gaussian kernel and an optimal number of the frequencies of the Fourier features. Found that around 1,000 of them is fine. So yeah, so the matrices I just showed you will be of dimension, well, number of data points that was somewhere in the 100,000s here, I think, times 1,000. We break it down to this 1,000 by 1,000 generalized eigenvalue problem. And after running through the usual analysis steps that you can also do with an MSM, we can indeed recover basically the assignment of all data points to folded or unfolded states using one of these membership decompositions here. So the point was just, the structure is known, yeah, the system is known, but we wanted to show that we can use the random Fourier features with the kernel on a rather generic feature space with a small number of hyperparameters that need to be tuned, the bandwidth of the shape parameter of the Gaussian and the number of Fourier features to arrive at an efficient model that reproduces the correct flow kinetics or folding kinetics of the model. Yes.
So your feature dimension is already fairly low. So I suppose that if you use the regular market state modeling approach where you do some dimensionality reduction and clustering, how would that compare to this? We generally see that there are better properties of this. We kept the spectra, the eigenvalues are larger in general.
So no, they are comparable to like to a very good MSM. Yeah, if you go through this typical MSM pipeline, you carefully select your TK dimension, you carefully select your clustering size, you carefully, maybe you even add an HMM estimation on top of that, then it's the same, or the MSM might turn out even a bit better. But I think the point was just to show that with relatively little effort, we get essentially qualitatively the same result. And that was the point. I also honestly, I don't expect this to remain that simple if you keep scaling the system up. I think at some point one will have to distinguish more carefully how exactly we choose these shape parameters and number of Fourier features. But I think still, due to its simplicity, it's an interesting and promising approach.
I suppose the advantage would be in the case where your feature dimension becomes so large that it's not really practical to do it with the regular approach, or where the degrees of freedom that hyperparameters we have the system.
Yeah, exactly. That would be my hope. Yeah, that if the number of features that you have to put into the regular approach is just too large, yeah, if you do the first TK step, then probably you'll just throw away too much. I hope that by going through this route of using the nonlinear kernel as a generic basis set from the start, I hope that this can yield better results eventually, if we find a way to tune these relatively limited number of parameters well. Yeah, that was all. So this is just to acknowledge my main collaborators and some of the manuscripts I talked about today. So once again, thank you all for coming and for the invitation, and I'm happy to take your questions.
You have any questions for Felix in the room or online? There's some people who are clapping their hands online.
Verify in the end, when you said that the system is known, to what extent is it known to the model?
Well, it's known that the slowest process is the folding unfolding process, and they're just reliable estimates of the folding timescale. And basically this plot here where we assigned all the time steps in the simulation to being either folded or unfolded, such plots have been reproduced consistently with different models. So there's consensus on what is going on. Yeah.
Oh,
yeah.
But the model itself goes just as a validation.
Yes. Yes, exactly.
Did you look closer at the other, because I suppose in this FIP35 there's a bunch of other metastable phases and folding intermediates and other shorter states. How does that compare to like a typical MSM?
I haven't looked too closely, but I think we have trouble recovering them in detail. Okay. That's exactly why I think that at some point, basically these parameters need to be chosen more carefully. Maybe I mean, at the moment we're using like a blank kernel, which is isotropic in all directions. I think this is probably too much, too simple for us as systems become more and more complex. I think these are the levers we can pull in the future.
Do you think that increasing the number of Fourier features would help you here? I mean, I guess that tells you the approximation error that you're.
It does, yeah. Yeah, I have again, I haven't studied it in detail. You know, it's something we should also do. My gut feeling is at the moment that something else has to be done.
Because there's this theory of like the projection error that you incur when you are projecting the operator. I suppose that's related both to the choice of kernel and now also to the approximation you do.
Yes.
Low rank approximation.
Yes. Yeah.
Have you analyzed this in more detail in this case? What component is the limiting factor? Do you have an idea of it?
So I mean, first we have shown that the number of features is exactly your EDMD dimension. So the entire algorithm in the end is EDMD with these complex plane waves as basis functions. Yeah, that can be shown. So I expect quite an quite an interesting interplay between those two parameters. I mean, if we stick with the Gaussian kernel for the moment, then it's clear that if you choose a Gaussian kernel that is too broad, it will treat all the data points as the same. So it cannot reasonably recover the slow eigenfunctions. Likewise, if you choose it super small, then basically any transition in your data set is metastable and you completely overfit. So there must be some relationship between there must be a sweet spot for choosing the shape parameter of the Gaussian, and the same should apply to the random features. But yeah, I mean, doing this analytically is well, we haven't done this, but this is something for the future. Yeah.
Any other questions for Felix? Doesn't look like it. So let's thank Felix again for a wonderful talk.